Good morning, everyone. Let's. Okay, guys, can you sit, please? Okay, thank you. Okay, so good morning, everyone. Welcome to the 2024 Brazilian ICPC Summer School. It's very nice to have you all here. Our school is promoted by the Brazilian Computing Society and Maratona de Programação, or Programming Marathon. It's organized by Unicamp, University of Campinas, along with the Computing Institute. This year we have as a sponsor Huawei as a premium sponsor. As a gold sponsor we have Unicamp and Institute of Computing and VTEX. And as bronze sponsors Profusion, Hyperplane, and Alura. And if you ask me what is this balloon next to the name, it means that VTEX paid for one female student to be at the school, Hyperplane paid for one female student, and Alura paid for 2 female students to be at our school. Okay? So this is a graph of the participation in our school. So we have this data from 2012. We were a little smaller than today. Since 19, we opened 2 classes. Now we have the World Final class and the Brazilian Final class. So our participation increased and stayed almost the same. In 2022, we have an online version, so it was the peak of the participation. And then it's almost the same number every year. And in blue, we have the number of World finalists participating in the school. So we have around 30 World finalists participating in the school. Okay. Finalists or Latino version? No, these are World finalists. Yeah. So for next year, since then you're gonna. This year we have also people from Egypt, classified to Egypt. So, but we also have a lot of Programadores de América classified here. Okay. Maybe we can raise hands. Who's going to Programadores de América? Okay. Yeah. Great number of people. Oh, sorry. So we have people from all over Brazil. We also have people from Argentina. Let me show hands. Okay. Chile. Oh, that's problematic because they wrote me yesterday saying how can I get to Campinas, and I gave them some instructions. But okay. Huh? Yeah, I know. I answered. Yeah. Okay. So I'm gonna worry about that later on. Colombia. Yeah, people from Colombia. Mexico. Okay, people from Mexico. Peru. Oh, nice. And Uruguay. Okay, nice. So we have people from all over Latin America, which is very nice for us. This is our female participation in 2019. We have only 8 female students in the school. So we decided to start funding the students, the female students, to come to the school. This started in 2020. So we had 15 funding, 13 not funding. In 2022, we didn't have funding because it was online. They had free registration, but they didn't need to move around. We didn't have to pay air tickets and so on. Last year, we had a little bit more than this year. Unfortunately, this year, we asked for a lot of female students that were in the Brazilian finals to come, but several of them couldn't come for maybe doing some internship or work or so on. So we had a little lower number this year. Let's hope that we can improve it next year. So the World Final class has 2 instructors this edition. So Professor Esquiena, which is here to teach you, oh my God. He's Distinguished Teaching Professor of Computer Science and the Director of the Institute of AI Driving Discovery and Innovation of the Stony Brook University. He wrote 6 different books, including the Programming Challenge, which I think many of you must know. I know that it was the book that I bought when I was an undergrad student to train for the programming marathon. And next week, we're going to have Michael Forisek, Mizov. He has 2 gold medals at IOI, 1 gold medal at ICPC, 1 bronze medal at IMO. And he wrote problems to IO, ICPC, and Top Coder. So we have 2 very nice instructors for you these 2 weeks. So what's the schedule for the week? Okay, except for Thursday and Sunday, you wake up. Then you come to the lecture from 8:30 to 11:30. Here at some point, you're going to have a coffee break, which is going to be served here on your left. Yeah. Then if you have your badge, you're going to have lunch at the university restaurant from 11:30 to 1 p.m. Then your contest starts at 15 past 1. Okay, and then if you have your badge, you're going to have dinner at the university restaurant. And then you sleep and you repeat every day until exhaustion. Okay? This is everything except Thursday and Sunday. Sunday we don't have any activities, but on Thursday we have some sponsor activities. So this first Thursday, we have a talk and activities by Vitex at 3 p.m. It's going to be in a different location, okay? We are going to send you instructions. It's not far from here, but it's a building where the 2 classes can be together. We cannot fit both classes here. Chile. Yeah. Oh, they are not missing. Okay, that's a big win for today. And then at night, instead going to the university restaurant, you're going to come here for a cocktail party, okay, without alcohol. Today, you are going to have the lunch going to be served in a different location because the university restaurant is not open. So it's going to be at the biology cantina, but the staff members are going to take you there. Don't worry. This lunch is sponsored by the University of Campinas. They are paying for this lunch. And at night, we are going to have a pizza party here on the back of this building, which some people call it Bosque do IC, or IC Woods. It's not like very like a woods, but okay. And it's this pizza party sponsored by Huawei. On next Thursday, we are going to have a brief presentation by Huawei in the same location that I mentioned before. And then we're going to have a talk from the Institute of Computing about graduate courses and so on. And then the last Saturday, we have the lunch in the same location that this Saturday, okay, also sponsored by Unicamp. We're also going to have an event on Wednesday night, this first Wednesday, for our female students. We are going to have some sponsors talking, Venturus, Vitex, Hyperplane, and Alura. And we are going to have some inspiring talks by Lucy, which is there, which is our head of sponsorship, Krishna, which is the leader of the women community, and Marília Gabriela Soares, which was a previous participant of the school and is a founder of a movement called Mulheres Univesp. Okay. So just to finish, I want to thank again our sponsors. Without them, we couldn't do this school. It's very cost to run this school every year, and they allow it to happen. Okay, make it possible. Our instructors from this class and the other class also, some of them which are present here, or all of them are present here, which the instructor in B. Computing Institute for giving us this space. Brazilian Computing Society for helping us organize and do the contability and so on, deal with sponsors and so on. The other organizers, there is Leilton, Lucy, Carlinhos, Ricardo Anido, Rodolfo, and Sandra. And all the staff members, anything that you need, you can find our students. There are staff members here that are going to make your coffee break, going to take you to the university restaurant, and so on. Okay, so anything you need, you can ask them. Okay, so this QR code, I think almost everyone should be there already, but it's the Telegram group where we're going to make announcements. So please join if you are not there. If you need anything, you can write to me, rafael@ic.unicamp.br. These are Google Groups. I think everyone is also there. Okay? But we can send some messages there. And please join us on Facebook and Instagram and some other social media. We are going to send them by Telegram later on also. Okay? So I hope you have a nice week. I would like to Carlinhos to talk a little bit. Yes, every year you make the same face. Yeah, and then we can.
Wish you a pleasant 2 weeks here. And let's start. I mean, you are waiting for him, not for me.
Okay. Let's see this thing. Okay.
Nice.
Very good. Thank you. Okay. Thank you. Can people hear me? Okay. Very good. Let me. Again, my name is Steve Skina. I'm very excited to be teaching this class, and my vision for today. Okay, it may change. We'll see if I go faster or slower than I expect. Is we're going to talk today a little bit about the organization of what the course is. I'm going to talk today about topics in dynamic programming for the beginning. Edit distance, which I think you all know and are tired of, and then advanced edit distance, which may be some ideas that I'm hoping maybe you're not as familiar with, that will I hope will be interesting to you. And then talk a little bit more about some string and pattern algorithms that are important. Again, depending upon if we have time, hopefully we'll get to things like suffix trees and arrays, and we'll see how this goes. So again, Raphael gave me a very nice introduction, and just so you know who I am, again, I'm a professor at a computer science department in New York, Stony Brook University, and I have for a long time was a coach of our ICPC team. We twice reached the World Finals went under my coaching. But probably what people know me best for are my books, okay? And have any of you seen or read any of my algorithm books or programming books? Okay, raise your hand, make me feel good if that's true. Okay. This is kind of where I come from. The red book is my algorithms book, which is, I think a good introduction to algorithms if you're interested. The gray book over there was the book that Raphael mentioned about my guide to kind of teaching programming, trying to get people started on programming contests. I'm pretty sure all of you are past this stage, but anyway, that's who I am. Now, I wanted to find out who you were. Again, I now know what countries you're from. Let me just make sure I understand. How many of you are still in high school? IOI type people. Raise your hand so how many of you are in the early parts of your college career? Okay. Now, how many of you are good. Okay, the final question I guess I want to get here is something about how many robot judge problems you have solved in your life. Okay, so there are these V-judges and these, code forces and all this kind of thing. How many of you have solved at least 100 problems? Okay. How many of you have solved at least 500 problems? Okay. How many of you have solved at least 1,000 problems? How many of you have solved at least 2,000 problems? Okay. How many have solved at least 3,000? Okay, we're now starting to wind down on this. Okay, so the reason I'm asking this is partially to explain a little bit what I'm concerned about in this class, okay? There's this question of, you guys know an awful lot about algorithms and programming from what you have done. Okay, and there's this question of what do you teach people who supposedly know everything? Okay, and I'm kind of picturing with all your experience, this is a danger. How many people know who Julia Roberts is? Is Julia Roberts a name? Okay, she's a famous actress. That's Julia Roberts over there. Okay, and she made a movie about, there was a movie she was in. I don't know if anyone has ever seen this. Has anyone ever seen this movie? Okay, very few people. It's a movie about this, Julia Roberts goes to teach at this art college. And she, the first day of class she goes to teach, and it's this college where everybody knows everything. And she goes to give the first lecture, she shows a painting, they know who did the painting. They know what year it was made. They knew what it was done. She does this for every painting on her slides. They all know this, okay? And so she says, oh my God, what can I teach them? And the next day she shows up. She shows up a picture, and she says, do you like it? And here they didn't have any answer for this. They knew what the names were. They knew everything, but they didn't have a sense of how things stuck together or what the taste was or something like this. So I'm going to try to teach you. My sense is you guys are largely, I'm going to say, self-trained in algorithms. You've probably learned by doing a lot of problems. And, my fear or my hope is that maybe there's some big picture aspect of things that I think is important that maybe you don't have as much. If you're learning these things by solving one problem at a time, okay? So my hope or my plan for this thing is I'm going to tell you how I think about algorithm problem solving in hopefully 5 different areas. I've got 5 lectures. I'm going to try to do this in 5 different areas. My other hope is that you will like it. If you don't like it, well, I'm still got a free trip out to Brazil out of this. At some level, it may not matter. But I do hope that this is true. Okay, fair enough. So what are the topics that I'm hoping to cover? And again, depending upon how the speed at which we do this and how this goes, today I'm going to talk about dynamic programming and sequence analysis, sequences. Next class, I'm hoping to talk about graph algorithms, things like network flows and matching. The third day class is going to be about what I call combinatorial objects, permutations, combinations, Young tableaus, set partitions, lots of different kind of combinatorial objects and how they come together, all around basically counting. And you'll see the power of counting if I do what I want to do. We'll then have a lecture on algorithms related to geometry, okay? And the final lecture will be about reductions between problems, which is, I think, important for learning to solve problems, algorithm, by mapping one problem to another, and also important to this theory of NP completeness, which I think is a useful thing to think about, even if it's not obviously on programming contests. And we will see about, I think this ability to do those kind of reductions is very important for programming contests. And that's what I'm hoping to talk about. Okay, now I do not speak Portuguese. This is one thing I'm going to confess. I barely speak Spanish, so the Chilean people don't count on that at all. I want a volunteer who will, I also sometimes don't hear as well as I would like. So I would like there to be a volunteer who will serve as a pair of ears for me to relay any questions we have. Do I have a volunteer? Okay, let me just look around for, let's see, you. Okay, you I think I want, prove to me you can speak English. Prove to me you can speak Portuguese. Okay, fair enough. Any questions so far? Okay, so my understanding is the day is I will start, that we have lectures till 11:30, and the, what you call it, the, there will be contests. These contests were set up by my graduate student, Tanzir Pial, so who's now at this moment watching this in Bangladesh, so hi Tanzir, and thank you for this. They are designed to be, I'll say, loosely coupled to the topic of the day, okay, and sometimes more loosely than others. Now, I want to just get a feeling for the class here. There are 3 ways we can do the lectures. One is that I start, today obviously you haven't had the contest yet. It could be that I don't bother to go over the contest at all, okay, or we don't discuss the contest at all. A second possibility is we discuss it at the beginning of the class every day. The last thing is we discuss it at the end of class every day. Who here would rather we just talk about lecture material and not talk about the contest problems? Exactly 0, okay? Who here would rather it be the first thing we talk about every day? A lot of you. Okay, who would rather it be the last thing we talk about? Okay, now I'm going to be trusting you guys to do a lot of the talking here, because I think when I coach my teams, what I would typically do is we will, basically give them a practice contest, then come back the next time, and I'll go, okay, first problem, what was that about, and how did that work? And that's kind of how I'm hoping to run the interactive part of that thing. Okay, now, for the contest, just to work this out in detail, should people be working as teams or individuals? Okay, I want to get it. First of all, I gather there's no scoring here. So this is all for learning, and on some level you should do what you think is best. I think that if you have a real team, how many people here are in teams that they're going to be part of? Okay, most. How many people here are not in teams? Don't be afraid, okay? Okay. I would probably encourage that if that's true, if everybody is here is in teams, I will encourage people to work within teams. And I will also encourage the IOI people to work in teams, unless I'm saying something that is very bad, if someone who's an IOI experienced person. For now, let's try working with teams. So I'm going to encourage you, if you are an IOI person, to try to make friends with ideally 2 other, okay, people, okay? And, you know, that way you have someone to talk to about what the problems with and try to work them out that way. And if this is a bad thing, someone who is more IOI experienced than me, talk to me at a break, okay? Any questions about the strategy? Okay, good. Okay. So what I'd like to now talk about is something that I think is everybody knows. How many people here know about the dynamic programming solution to edit distance? How many people don't? It's not obvious that you do. Okay, a few. Very good. Okay? I'm going to try to go through this, you know, relatively fast, but I want questions. This is important to me because I don't know what you people really know or don't know. And it will be very helpful to me if there are questions in the course of our day. So what is the edit distance problem? The edit distance problem is a problem where you are given a, do people see my mouse if I do this? Okay, so maybe that's my pointer. You have 2 strings, and you would like to figure out kind of what is an alignment between the 2 strings, where you try to find the best possible commonality between one string and another. And the way we measure commonality typically is that there are 3 changes you can make to transform one string into another. You can do a substitution, okay, of a character. Like here, the T became an L. You can do a match where the characters are the same and in the same order, okay? And you can do either an insertion or a deletion, okay, by either deleting one from the top string or adding it to the bottom string, okay? And edit distance is finding the smallest number of changes you need in order to transform one string to another. Okay? Any questions about that or anything? And the way that you solve this is with dynamic programming, which I'm assuming, obviously, most of you are quite familiar with. What is dynamic programming? It is a technique of an algorithmic technique where you solve, basically you solve an algorithm by basically computing a recurrence relation, a recursive formula, okay, a formula that depends upon itself, by storing partial results. And again, I know you know a lot. Dynamic programming is very powerful whenever you have ordered structures, things that have a sequence to them, like character strings, like the nodes on like the leaves on a binary tree. Okay, there typically is an order from left to right. If so, dynamic programming is a good thing. Okay, how does dynamic programming work? Basically, you build a table where every cell, okay, in the table is going to reflect the cost of getting there. Each cell is going to be defined by a prefix of the items. This kind of the state of the recurrence relation. in edit distance, the recurrence relation has two parameters. So the table has two parameters. And typically what you're going to store in there is a cost and a pointer back to how you got to this cell. That's kind of the other thing that typically is involved. Okay? When you implement the, in edit distance, the recurrence relation is that when you have two strings, and you're matching one string to another, let's go back to our picture, something had to happen at the end of the string. It had to have ended either on a match, or a substitution, or a deletion. If it ended on a substitution, you have up till now aligned all but, if it was the ijth cell, the first I characters, up to the first J characters. Actually, well, let me just, they say the blackboard works. Let's just write down the recurrence just to make sure we understand it. That I'll say M of ij is going to be the min of three options. One was that we ended on a match or a substitution. Okay. One is we end on a match or a substitution, in which case we have to pay for the cost of aligning the last characters of the two strings, plus the cost of getting there. Or we end on an insertion, in which case one of the arguments gets incremented but the other one doesn't, and we pay the cost of doing an insertion or a deletion. I call it an indel cost. Or it's the other way around. And we pay the cost of an insertion. Any questions about this? Especially from people who weren't familiar with this, because I know many of you have eaten this forever. Okay? What is the case? In general, let's assume that it costs one character to do an insertion, one character to do a deletion, and either you match, in which case you don't pay anything, or for a substitution, transforming one character to the other one, you pay one also. So if so, you then write a dynamic programming out implementation. That's kind of what we have here. Here you see the structure of the recurrence relation. Encoded here, we figure out for every cell from I to J, what was the cost of ending on each of these three options. We store as the cost for the cell ij the minimum, the cheapest way of getting there. And that's basically the heart of this algorithm. Any questions? Comments? Okay. Bang. And again, you have to initialize the rows and columns properly depending upon exactly what you do. But that's not my main goal for now. Basically, what you get in aligning through strings is going to be a matrix, okay, where for every prefix of one string and every prefix of the other string, you get the cost of what it was to edit that prefix into that suffix, okay? And that is the what is kind of stored in this dynamic programming table. Okay? And the ultimate cost of doing this is the value of the last cell in the right corner. That's the cost of, if you want to update the Bible, instead of it saying thou shalt not do things, you want it to say you should not do things. It takes 5 character changes to do that. Any questions? Okay. The other component here is that there is this, in order to figure out store what decisions were made, you need another table or another field in every cell of the record, telling you where you came from. Did you come from an insertion or a deletion? If so, that was a diagonal move. Okay? If you came from a deletion down, a substitution, an insertion down, that was, I guess, labeled 2. If it was a deletion across, that was a 1. The parent matrix told you where you came from. Any questions about this? Okay? And once you don't have that parent matrix, you can reconstruct what the alignment is in the edit distance by walking backwards and reconstructing the decision. We go back to thou shalt not and you should not. How do you know what was the changes that were on the optimal alignment? You could, again, the cost matrix told you the cost of editing something into something. The cost matrix by itself does not tell you how to get there. When you have the parent matrix, okay, you start from the cell 0 meant diagonal. As you can see, the heavier letters. By walking backwards recursively, starting from the end cell, saying 0 meant diagonal, I go there, go there, go there. 1 means go to the side. 0, 0, 0, 0, 0, 0, 2 meant up. Okay, I can reconstruct the alignment and find exactly where there were insertions, deletions, and substitutions. Any questions about that? I assume this is all obvious to you. Okay? Any questions about edit distance? Okay, good. Let's now talk about more advanced edit distance. Okay, things that may not be quite as obvious to the people in this room. Okay? How much space does it take to, if I wanted to do the alignment between 2 strings, one is of length n, one is of length m, how much space does it take to do that? Okay? Where is the space in my dynamic programming? It's my table size, right? When I have an n by m matrix, or obviously it takes n by m cells, how much space does it take if I want to save space and find the edit distance between 2 strings? Someone with a, yes?
Like, if you want to so we can probably do like O of n.
Okay, so you're saying to me, I don't need this whole matrix. You're saying to me, I only need to store, because every one of these cells only depends upon the one above it, to the left of it, and to the diagonal of it. I only need to know the previous row. Does everybody agree with that? That would say that if I have it, in this case, an n by m matrix, I only need order m cells, depending upon the size of the, assuming m is less than n. Does everybody agree with that? Okay, that's also very simple. But let me now ask you this. Suppose I want to reconstruct the optimum alignment. How much memory do I need? Okay, this is now one I want you to think about, okay? Because this now is not suddenly so obvious anymore. Okay, let's think about it for a second. Why isn't it obvious, first of all? Because it would seem you need to store the entire matrix of parent pointers, because you're starting from the, if you wanted to reconstruct, I guess I keep going back, if you wanted to reconstruct the alignment, you had to go follow from here to walk up, walk up, walk up. Which is the optimum path when you're building this dynamic programming thing? Do you know when you are making these cells, which cells are on the optimum path? The answer is no, okay? Because they are, they're all potential possibilities. the optimal alignment is some path. If you just store the last two columns, that will tell you how to get up to here, but it doesn't tell you how to get further back. Does everybody see that? So how much memory do you need to reconstruct the optimal alignment? Do people see that this is now an issue? Yes. O of n. Well, now n is, you're saying n is bigger than m.
The minimum of 2.
I think you need the maximum of the two. Well, actually, no, you need the minimum of the two.
No, because the path itself.
Well, let's just figure this out again. Hold on a second. Actually, let's figure this out, okay? How can you possibly reconstruct the alignment here if you can't store the whole matrix? That's right now the question, okay? Okay, yeah? You can run the algorithm n times and do it again. This sounds expensive. Okay, you're saying it sounds, you're saying somehow run it many times and then you will know what the right answer is. Can you do it, reconstruct the right solution without actually spending more time? Okay? Let me show you how you can do it. Okay? And this is one where maybe it is an interesting idea. First of all, when it comes to dynamic programming, the amount of memory you use, it will certainly in real life, maybe not always in programming contests, the amount of memory you use in a dynamic program will kill you faster than the amount of time. What happens if you want to run an algorithm that is n squared and you really want to do an answer, get the answer? What do? You wait, okay, and it'll eventually finish. What happens if you want to do something that takes more memory than you have? What do? You wait until you get a bigger computer, right? So there's a difference here. So how can we solve dynamic programming, pretty much any dynamic programming algorithm, okay, in optimal time while using only linear space? Okay? And the idea here is the following. It's something called Hirschberg's method. Okay? If you remember, what was the information we kept on every cell in the dynamic programming, the one I had originally? I stored the cost, and I stored what the parent was, right? I'm now going to store a third thing, which is what was the row, okay, where I crossed the midpoint, okay? Now, what does that mean? If you look at this, if you, in a dynamic programming thing, maybe I'll even try to use the blackboard. In a dynamic programming thing, you know we saw before that every cell depended upon those three. So we know where it came, where every cell came from someplace, right? Now, at some moment, you're crossing the midpoint, okay? And from this cell, I want to now know what row did I cross the midpoint at? Well, for each one of the cells in the median column, they cross the midpoint at the corresponding row, right? Now, what about a cell that depends upon it? This cell over here came from either here or here or here. It will inherit what row it crossed the midpoint from this one, right? You're getting the parent. You're going to basically get the cell you crossed the midpoint from your parent. The cell that you crossed the midpoint was the cell your parent crossed the midpoint. Does everybody get that idea? Okay. Now, what do? Suppose I now do my space-saving dynamic programming, only keep those two columns thing that you were doing a minute ago. What do I now know when I get to the final column here? I know the cost of editing the two sequences. I know what was the previous step, but only one previous step, because then I go into oblivion because I forgot all that. And I know what row I crossed the midpoint at. Does everybody see that? So what does that mean? I now know basically this point, okay? I know what was the row where I crossed the middle column, okay? On the optimal path to align the two strings. So what can I now do? I can recursively solve from the beginning point to the end cell and find the best possible path. And I can recursively solve from the midpoint to the absolute end cell. Okay? And the union of these paths is going to be the optimal solution. Does everybody see that? So I'm going to solve this recursively, and I'm going to reconstruct the path bit by bit. Okay? But what's this going to cost me? Any questions? How many people see the idea? Okay, I like this idea. How many people don't see the idea and want me to explain it better? Okay? Is there a particular question that you can have, or just don't see what it's doing yet? Okay, one of my ears, what did she say? She doesn't know how to retrieve the, she's going to retrieve the path bit by bit, okay? Let's think about this. We had this recursive thing. By the time you got down here, what do you know? You know, I guess, the previous step, but only one step, right? And you know what column, what row you crossed the middle column. You know the path started from here. You know, it went through the middle here, and it ended up there. So how are we going to reconstruct it? If we now recursively align the strings, what are we now going to do? We're going to find out what was the middle cost part here. And now I've got that bit of my path. And when I recursively solve this thing, I'm going to get this part of my path. And then I'm going to recursively do it again. Okay? And one step by one, I'm going to reconstruct the path. Does everybody see that? Okay? In disjoint pieces that are getting stuck together. Okay? What's the time that this takes? Okay? One of you guys was complaining about, oh, it's going to take me more time, I'm going to have to spend more time. Is this going to cost more time than doing it once? You're saying, wait a second, you're doing it many times. How can it not cost me more time than doing it once? This is the magic of kind of geometric series and convergence and a half and a half and a half. Notice that when I took this matrix here, wherever the midpoint was, the parts that were relevant to finding the future path were exactly half of the original matrix, right? Once I know this is the midpoint, this part of the matrix has no value. This part of the matrix has no value, right? So solving these two is going to cost half the time of solving the original. And then once I found this, it's going to find half the time of solving the original. Okay? So what is the analysis here? The real runtime analysis is going to be this. The sum, as I goes from 1 to the logarithm of my size of my matrix, okay, in each round I go and break this thing up, I'm doing half as many cells as in the original solution. A half plus a half plus a half doesn't get you any further than where you started, right? So the total time is still order mn, even though you didn't need to use the extra memory. Okay? Any questions about that? Do people kind of now understand the scheme? Okay? And this is something pretty general that you can do with a lot of other dynamic programming algorithms. Okay? Taking advantage of the exponential convergence, okay? And the miracle of recursion. Any questions? Okay, good. Okay, yes, your question, yeah.
This works because the EBC algorithm is n squared. If it were linear, it wouldn't work because the recursion would be more expensive than the algorithm itself.
If this was order, you're saying if it was linear, it wouldn't work. No, this trick should still work, even if it's linear. Because if you think about dynamic programming, the running time here was linear in the number of cells. The number of cells were quadratic, but the number of, the running time of dynamic programming is linear in the number of cells. The key thing is the number of cells gets halved each time. And if you could imagine some kind of a one-dimensional dynamic program, that I had to reconstruct some magic that I was doing on this, it's still the same thing, provided I find what the step that's in the middle of that, and then I throw out, the appropriate half. Okay? So, okay. Any questions about this idea? Okay? Yes? Let's say you were building again, I'm trying to think in a linear DP. Maybe you are, okay, so let's say maybe you're building some kind of a subset of things. Like there's a certain number of cells that are where you're placing, like what might be a normal one-dimensional DP that might be interesting. Maybe something where you're reconstructing a subset of interesting positions, okay? Maybe like in an integer partition thing, you were trying which elements were you taking to add up to something. So that would be a linear type of a thing. And again, if you want the claim would be that in this reconstruction, it's clear that what I am doing is linear in the number of cells. Therefore, I see no reason why such a step wouldn't necessarily work in a linear one. Although I'll admit I'm now not coming up with a great answer here. Yeah.
Like if you have a linear DP, when you split it in the middle, you don't have number of total cells, right?
Let's say you were trying to find where some magic item was. Okay? It still seems if the magic item is either on the left or the right. Okay? Maybe. Okay, let's say we're not going to make any promises for linear problems, okay? But it should be clear it's working here, okay? And if it's working here, it's not doing anything that seems so profoundly edit distance-like, okay? That this is it should be a reasonably general technique, okay? Any questions about this? Yes?
I didn't understand well how to compute the point where the path crosses the middle column.
Say this again, I'm sorry.
He didn't understand how to calculate the midpoint, like when you close.
Okay, how do you know what the middle column is? It's easy to figure out, because if this is an n by m thing, what's the middle column? That's m over 2. So knowing what the middle column is easy to do. For each element, you're going to have, for each element in the cell, there's going to be 3 things in the cell. There's the cost, there's the parent, and there's the mid row. what was the row where you crossed the middle column, okay, to get there? Now, on this side of the river, on this side of the middle column, what middle column did you need to cross to get there? None of them. It's unknown. At the middle column, it's obvious. If you're in row I, cell IJ, it's I. Okay? And from then on, you're gonna inherit it as you walk along there. That's the idea. Okay? Any questions? Okay, very good. Very good. Okay. Let's talk more about edit distance and some other things that become interesting. What is the cost of editing strings when the strings are very, very similar? Okay? You could imagine a world where sometimes you're editing, you have two strings that are n times m. Maybe the edit distance is very, very small. Okay? Do you have to spend n times m time in order to compute what were the number of changes from this to this if the strings were very similar? Okay, does everybody can? What are two strings that are very, very similar? Let's say you're taking an exam, you're writing your paper out, and a not good student next to you is copying it, right? They may make a spelling mistake every once in a while. But the edit distance is very small. How would you find the optimal alignment when you've got two strings, n of length m, and the edit distance is only k? Okay, do we still have to spend n times m time for this? Okay, how do we do this so we don't spend n times m time? Okay, the picture may give you some idea. Okay, if the edit distance is of order k, okay, if it's k changes from one string to another, what do we know about the optimal alignment, Beth? It can't be more than k steps from the main diagonal. Does everybody kind of see that? Okay? So, if that's true, the only part of the matrix that you really care about is k steps from the main diagonal. Okay? So how do you take advantage of this when you don't know what the edit distance is in advance? Okay? Suppose you want to edit two strings, find the cost of editing two strings. You think maybe they're similar, but they're not necessarily similar. Is there a way to compute edit distance in time that is going to be order k, even if you don't know what k is in advance? Okay? Any ideas?
Guess a upper bound of 5 or 2.
So
You guess 2, 4, etc. until it's bigger than k.
okay, so you guess an amount, and you want to do some kind of like a binary search almost in order to figure out what that edit distance is, right? Now, it's not pure binary search because of the way that he said. It's something called one-sided binary search, okay? My claim is if I have an n by n string and there only is a distance of k changes between the two strings, I can do the edit distance in order k times n without knowing k in advance, okay, by guessing repeatedly what k is. Maybe k is 1, maybe k is 2, 4, 8, and keep trying it now, okay, assuming that k is right. What does that mean? That means that I've got a matrix, once I guess k, I'm only going to look at the cells that are k to the left of the main diagonal, k to the right of the main diagonal. Those are 2 times kn cells. Does everybody agree? How do I know whether I have used a wide enough band Or maybe I need to use a wider band. Okay, we agree I can keep doubling it, try k equals 2, 4. What is the condition to test whether my band is wide enough? Okay, yes? What? So what you're saying is if the cost is, if let's say I enlarge the size of my band and the edit distance didn't change, that's what you're suggesting as far as I can tell. Maybe not. Okay, is there a way to tell what it would be? Yeah.
Even though less than you guess, then you can be sure that it's correct.
If I got a larger band, okay, then if I got a cheaper cost, then making it wider helped. But what's the criteria under which I know I can stop? What?
The answer is not infinite, you can stop right.
Okay, so as a question saying infinite, well that depends upon kind of what boundary conditions I give these cells. You're saying that if there's a, if the cost is not infinite, okay, well that's not completely true either. Because I could always, for example, edit the two strings by substituting a lot and never get to these infinite cost cells on the end. Right? If you think of a world where you're saying I'm going to set the cells out on the boundary here that I don't want you to cross. I'm going to set them to be infinite cost. Okay? What is the criteria? Let's think about this. Okay? This is something to think about. Okay, yeah?
If the cost you get is equal to the k you guessed.
What I would say is, if there is a solution whose cost is less than the width than k, the width of the that I have done, then that's the optimal cost, right? If I have a solution which costs k, and I have at least k cells on each side, okay, then I can't come up with a cheaper cost by wandering further away from the diagonal. Okay, this is, I guess, the argument that I want to make, right? If you find a cost that goes substitute, bung, 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 it would be expensive. But if my band of size k is of size k, and my cost is less than the width of my band, I have found something that is less than has never traveled more than k positions from the main diagonal. And any path that travels more than k cells that would take advantage of the cells I haven't looked at, those would have to be more than k from the diagonal, so the total cost would have to be greater than k. Do people get that idea? Okay. Good. Okay, so there is a faster way of doing this. What's the total cost of this algorithm? I'm going to try it with k equals 1, k equals 2, k equals 4, k equals 8, so many times. I might run this log, I'm going to run this log k times. What's the total cost of this algorithm? Okay. I claim this is the exact same idea that happened with Hirschberg, right? The sum of doing n times k equals 1 plus 2 plus 8 is always going to be less than twice that of the largest term. So if in fact the winner comes up with a band of k, I'm going to look at n times k cells there. The total cost of all the previous things is also going to be at most n times k. Does everybody kind of see that? Okay? And so this gives me a way to do edit distance, which is going to be the same in the worst case time, but faster in the, if the strings are very similar. Any questions? Okay, just a quick status check. Who here thinks that I am going too fast? Be honest. Who here thinks I'm going too slow? Be honest. Who here says I'm going just right? Then everything is right, okay, good, okay? Then everything is so far very, very good. Okay, any questions about this part of edit distance so far? Yes?
If you want to reconstruct the path, can you do the same optimization for memory?
So now the question is, if I want to, can I now use Hirschberg's algorithm to do it? And I see zero reason why not. Okay, let's think about it. Okay, what would be the case here? Okay, oh, I guess I don't, okay, that's my picture there. What would be the case now? Now my matrix is looking sort of like this. What do I want to know? What was for this cell, which was my optimal cell, where was it that I crossed the main diagonal? Now this then becomes, maybe this is not so obvious now. I'm going to find what row did I cross it. What do I now need to do? I now will have this cell, okay? I will have this cell. I will have this cell. I now have to recursively solve it as before, okay? But what do I know? Have I thrown out half the cells that I had before? No, I did not throw out half the cells as before, right? Does everybody see that of the cells that I had been counting, which was my NK cells, I am keeping more than I'm throwing away, okay? So can I do this in the sense of will it be correct that I will come up with reconstruct my path? It will still be correct. Will it still be order n times k? That is not obvious to me here. Yes?
But doesn't the band get way thinner on one of the quadrants?
It could be that one band keeps like the same size.
Okay, so now if we want to try to invent something, is there a different place where I would like to go? So what you're kind of saying is there a point where instead of memorizing where I cross the midpoint, you're sort of saying maybe I can memorize two different things, which are going to be a place where when I cut anywhere on here, okay, I will cut off a constant fraction of the cells. Okay? That might work, okay? That maybe requires a little more conception to really prove than I want to do standing up. But that's an interesting idea. Does everybody see why that kind of an idea is necessary? Okay? Because for the recurrence to the geometric thing to work, we had to constantly have things. Okay? And when the shape is no longer a rectangle, we don't get that property for free. But it could be that maybe there is a point where, instead of at the midpoint, where we will be able to break it into a small number of pieces, each of which, a constant number of pieces, each of which will have that property.
Just like store which point is the point where you had like half the edit distance. Like after you find the edit distance, you find the point where you half the edit distance. Like if this is scale, you find the point where it's scale over 2, and then you are now computing something that now each half only has edit distance k over 2. So instead of n times k, you're running n times
Okay,
over 2.
you're suggesting that you do the partitioning based on where you actually hit half the edit distance. This I don't think I like, actually. Because again, the goal is to throw out half the cells in the matrix.
Yeah, but now each half, now you don't need to store the whole band for the whole matrix. You only need to store the band where it's k over 2. Right? Because each half only has added distance k over 2. So for each half, you only store a band of size k over 2. So for the whole matrix, if you sum all the bands, it's only going to be k over 2 times n.
Okay.
But is it easy to
Yeah. You first find the edit distance, then you find the half point.
any
Maybe you could also
state
see
that
which.
has K over 2 edit
like-
distance because it might not be on the optimal path.
Oh wait, I didn't hear them.
Is it easy to find that point? Because you can't just take any point with edit distance K over 2 because it might not be on the optimal path. Or many points.
No, but you store, like, you first find the edit distance, then you do a second, algorithm where you also store which one is in the middle of the edit distance, like,
Yeah.
which point hit the K over 2.
Yeah, but when you find a point that has edit distance K over 2,
Yeah.
you don't know that going forward, this will also be in an optimal
Yeah, you
path.
started in the DP, like the other attempt.
Okay, let's say, this is something that, what I will say is this is delicate enough, I'm not doing it standing up, okay? But I think it's good that you're to the point where you're thinking about this kind of thing, and we recognize why it is not immediately obvious. Again, that's what I think is the takeaway, okay? Is that we have to be able to throw out a constant fraction of the cells regardless of where that midpoint is. Okay, and this is what I'm not feeling certain about with the kind of arguments that you're doing. Okay? Any questions about this? Okay? Okay. So if the string's similar, we can do better, and that's the kind of banded alignment thing. Okay? Okay. Let's try one other notion of edit distance that's kind of important here, which is what happens if we're doing edit distance where we want to, again, in a lot of times when you're comparing two strings, you're trying to, you're trying to figure out how similar, where were the changes made, okay? In many edit distance applications, you have an operation where you might delete a large chunk, okay, of a text. So actually, I'll tell you, with one of my grad students, actually the same graduate student who I mentioned before, Tanzir, we had a paper recently where we were looking at how did you find what sections of a movie script what sections of a novel did not appear in the underlying movie. Okay, so you can imagine a world that there is a movie, there is a script, the movie is 800 pages, the movie is 2 hours, okay, something's got to get deleted, right? And if you wanted to measure the deletion, how many changes were made between the movie and the script, does it make sense to count how many characters were deleted from the book? Or does it make sense to talk about how many chunks were deleted from the book? Okay, I think guys are into chunks, right? You would like to say, oh, this chapter, they cut out this chapter. This character, it was nowhere to be found. Okay? So let's now imagine a world where we're doing edit distance, but not on these character changes, but on chunk changes. Suppose I want to know how many pieces of the text, what's the smallest number of pieces from the movie you have to delete to get the script. Okay, does everybody see how this is a edit distance? It's different than edit distance with, as you've been learning on the character level, because the cost of deleting a long chapter is going to be proportional to its length, as opposed to one whoosh, whoosh, to take it out, right? How do we find the smallest number of deletions, or so-called gaps, that we have in doing the alignment of the text? Let's think about this, okay? Do people see why doing just single deletions is not the thing to do here? Okay? So instead, there's a more general form of edit distance where people deal with what they call affine gaps penalties, where the cost of a penalty, if I'm deleting a chunk of T characters, the cost that I'm going to pay is A, one cost for starting the deletion of the gap, and then B for every character I delete. Okay? Now, if I don't want to pay, if I want the cost of a big deletion to be the same as the cost of a small deletion, I said B equals 0. Does everybody see that? And that'll do what I want. Okay? How can we do edit distance where we're trying to keep track of, minimize the number of chunks that are changed, rather than the number of actual character changes? Does anybody see how to do this kind of thing? Okay, so think about it. Let's think for a moment. If you kind of see what I want to do, I want to find the minimum number of chunks that I'm changing, rather than the minimum number of characters. Is there anything that you see how I can do this, knowing what you know about edit distance? You.
So instead of jumping one cell up and one cell to the left, you have to jump any number of cells up and any number of cells to the left.
Okay.
And if you can pay an extra linear cost, you can do all those jumps and calculate the cost for each jump.
Okay. What I think this gentleman is coming up with is this idea as follows, and you correct me if this is not what you're thinking. Okay? Suppose you guys knew about edit distance. You knew that we were talking about things. Edit distance, there is still this prefix function. The first I characters of one, the first j characters of the other. We're going to say that at end ij, there are three possible ways. Vij is going to be the cheapest way to get to the end of the string. The way we can do it is, we can either end on a match or a substitution, that's that you've seen before, or we could end on an insertion, where we're going to be inserting a bunch of different characters. J minus k, okay? So we have k iterates from 0 to j, and we try over all possible numbers of deletions. Okay? So if we end on an insertion, we're going to have to figure out how many characters are we inserting. If we're inserting k characters, that's kind of, I guess, what you're trying to do here. We try over all k, and at each step we minimize. What is the cost of getting to cell ik? Okay? Plus the cost of deleting the last j minus k characters. If we're only paying 1 for the gap, indel is going to, of any size, is going to cost 1. Does everybody see that this is what would handle for the insertion side? There's the symmetric thing for the deletion side, where our argument, again, this was the second argument, this was the first argument. He's suggesting that this is the approach you're suggesting, right? What is the running time of this algorithm? Okay, first, before we get to the running time, how many people understand this recurrence? Okay, do people understand it? How many people don't understand the recurrence? Okay, so what is the idea here? Okay, let's try to maybe draw a picture. This is it. No more band. Okay. The idea here is, if we have our edit distance matrix, and we're at a particular cell, okay, to get to this cell, maybe we decided to delete this entire chapter. If so, what would the parent of this cell be? It's going to be right back here. Does everybody get that? And the cost of this would be, in the case where that beta cost was 0, it was going to be 1. In order to figure out which is the size of the jump that is best, we've now got to evaluate all of these cells. Does everybody see it? And the cost is going to be the cost of deleting something, a gap of a particular size, plus the cost of getting to that cell. Okay? And so in order to do this, we're going to have to look at all values of k going up this way and all values of k going that way. Okay, and that's what you see on my recurrence here. See, I've got a min of k goes over this, k goes over that. Any questions about this? Do people now understand what this is doing? The recurrence is basically doing? What is the runtime here? Now if we're doing edit distance, this was n, this was m. If we wanted to pay the minimum number of cost, the minimum number of gaps under this thing, what is the running time of this recurrence? Cubic, okay. It's because for each of, the way I think of it, for each of n times m cells, how much am I going to pay? The max of n and m, or I usually just say n plus m, just to be polite, okay? But this would be, if n and m are the same, this is cubic, right? Do we need to spend cubic time on this, though? Let's think about this. Is this really a cubic time algorithm problem? Or is there a way to get away with this in less than cubic time? Okay. Any ideas? Yes.
I mean, you need a data structure for each column, for example, to compute that minimum efficiently. If you're using the affine rule, I think each time you add a new element to the column, if it's the best, then it stays the best forever. So you only need to keep track of what's the best in that column to jump to.
Okay, so what seems clear is we want to figure out some way to know to avoid doing all of this search. That's clear. That's clear that the win. If we want this to be fast, we've got to avoid doing that search, right? How can we do that? Well, what if we actually add a couple of elements to our recurrence? I don't know if, can you guys, is this visible, by the way, from where you're sitting? Or is this hopeless? Okay, so you guys should know next time you sit in those chairs. Okay? What is the idea here? The idea here is we're going to add sort of some complexity to our recurrence by basically figuring out modes, okay? You kind of could either think of every cell. What information would you like to know about at this cell to avoid doing all of that insertion stuff? Okay? My claim, I'm not going to write it on, it's not the way it's written on the recurrence, but let me tell you how I'm thinking about it. You could kind of now think about what is the cost, I guess, what do I call big M, of ij, and I'm going to say the mode. Okay? What is the mode going to keep track of? What are the possible situations that are interesting? One is you are just ended on a substitution and you're not in an insertion or a deletion. One is you ended on an insertion or a deletion. If you ended on an insertion or a deletion, you've already paid the price of starting the insertion and the deletion. Does everybody kind of get this idea? If you've already paid, sort of like, I don't know, you can imagine going into some kind of a club. Once you've paid, you're in, okay? So what is the story going to be? The modes here are, the last thing we did was a substitution, or a match. The last thing we did was an insertion. The last thing we did was a deletion. Okay? If we already were in a deletion, if we're coming from here, so here we've got a cell. If we know are going to do another deletion to get here, if we're ending up in a mode where the deletion was, we were in deletion mode, we would be paying only the character cost of getting from the previous stage here. Okay? If we were coming from here and we were in insertion mode, we would only pay the cost of that last character insertion, not starting the run. Okay? So what's interesting here, in the way I'm framing it, is there is a prefix for each string, and there's a small number of possible modes you could be in. Either you ended up on a substitution or a match, meaning if you want to do a deletion, you're going to pay the cost of deleting a whole run, even if you're only deleting one character. It could have been you were already in a deletion mode, so you only pay for deleting that one character. Or it could have been you were in an insertion mode, in which case you only pay for inserting one character, not starting a new run. So what is the recurrence relation? TV person, if I walk over there, are you going to see me? Or it's, okay, let's see this. Okay? What does this recurrence look like? Okay? If you look at it in here, in two of these modes, you are paying the cost of starting. These are the insertion and deletion modes, right? In order to pay, what's the optimal way of editing the first I and J characters ending up in insertion mode? Well, if you were already in insertion mode, it's only the cost of adding that one character there, right? If you were not in insertion mode, you have to pay to start the insertion. A is the cost of starting the insertion run. A is the cost of starting the deletion run. Okay, do people see what I'm kind of doing here? Now the cost of every cell is only going to be a choice of two possibilities. If I'm going to end up on a deletion, either I came from previous deletion mode, in which case I only pay B, or I was previously in a match or substitution mode, in which case I pay the cost of starting the run, which was A. Does everybody kind of see this thing? Now, what is the cost of this algorithm? Okay? How many cells do I have in my matrix? N times M times the number of modes, right? Which is 3 or 4, some constant thing, right? And how much time does it take to update each one of these things? Before it took order N to update each one of my cells, right? Now how much time does this take? Constant. Does everybody see this thing? So now, again, by keeping track of these modes, this is actually the real trick. It's easy to get lost in the symbology of the recurrence. But the idea here is that keeping track of the modes, okay, if you have a constant number of modes, you can do that as part of the, and it doesn't add to the big O complexity here. Any questions about that? Any questions about why gaps might be an interesting thing to do? Okay. Now, I am told I should not, is the coffee break here? Okay, we can either keep going or you can have your coffee break. Who here says the coffee break? Okay. Who is so eager that they want to give up coffee? No one. Okay. Why don't we stop it here? Okay, and we'll continue on with advanced edit distance when we come back. Thanks for your attention. any questions from the previous lectures or anything like that? Okay. Okay. The other thing, one thing several students have asked me was, where are my slides? Okay, and I have given my slides to the organizers now, and these I gather are being sent out on the Telegram on some secret channel you guys have. I will also, if anyone is watching this in TV land, I will eventually put these on my home webpage at Stony Brook. So, or on my algorithms page. Okay, so if you go to my algorithms course, they will eventually be there, but not imminently. Okay, so we had been talking about kind of advanced edit distance. Again, I think that was a good session before. I've convinced you that the simple dynamic programming edit distance thing has more complexity to it than maybe we might have thought at the beginning. There are a couple of other areas of edit distance complexity that I would like to talk about today, and we'll see whether this how far we get here with this. But one question that turns out to be important in biology, particularly, but in other applications, is this idea of what happens if you want to align more than two strings. We have been talking about edit distance. In edit distance, there are, there is string S and string T, and we built our matrix. If you look at the example I have on my slide, you can imagine, obviously there's a version of edit distance that I'm sure you guys know called longest common subsequence, which is just edit distance where the cost of doing a you make the cost of a substitution impossibly high. If you make a cost of a substitution impossibly high, the cheapest way to align two strings is to only do as many matches as you can, because anything you don't match, you have to either insert or delete away. So here is an example of a problem of essentially longest common subsequence when you have more than two strings, okay? If you look at this, here on the left I've got 5 strings. On the right I have demonstrated what the longest common subsequence between all of them is, and it turns out to be hidden words, okay? So you can see that the thing on the right is the string, the longest string that is common as a subsequence in all of the input strings, okay? For 2 of them, you know how to do this, because this is just dynamic programming. What if I asked you to find the longest common subsequence in 3 strings? How would we do this problem? Now I give you an S, a T, and let's say a W. How do we find the longest common subsequence of those? Does anybody have an idea how you would do that one? Okay, what changes in our world? Okay, when we go from 2 to 3. Okay, well, we add 1. That's what changes. Okay, how would we now do an edit distance type of thing with 3 strings? What is going to be the key thing that changes? Okay, this is supposed to be simple. Yes. What? The dimension of the dynamic program. Now, if I want to do it, it's going to be something like M of I, J, K, which is going to be equal to what? That's going to be the longest common subsequence of S1 dot 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 to I, T1 dot dot J, and what do we, STW from 1 dot dot K. Okay, does everybody see now? So what is the complexity of finding, if I have 3 strings of length n, what should be the complexity of longest common subsequence for 3 strings? Should be n cubed. Does everybody see that? What about if I have 4 strings? Fourth, n to the 5th, dot, dot, dot. Does it continue exactly like that? Well, not exactly like that, okay? What is the complexity here? Well, first of all, it should be clear. The recurrence is what we say it's going to be. The state of the recurrence is going to be, as you see on my slides, okay, that if I have k strings, there's going to be a k-dimensional, recurrence, and the number of different cells in my thing is going to be n to the k. Okay? Now, what is the actual recurrence going to look like? Okay? It's going to be a little complicated for me to, too complicated for me to want to write down. But what is the idea going to be? I'm going to look at, for every set of, if I have a particular value of I, j, and k, what am I going to ask? I'm going to ask myself, is the, do S of I, T of j, and W of k, are they all the same character? If they are all the same character, then I am going to get the length of the longest common subsequence ending here is going to be 1 larger than the largest, longest common subsequence of any cell that it dominates, okay? What does it mean by dominate? Okay? I am going to say that by dominant means that on one of the, at least on all the dimensions, the cell is going to be less than this. So in other words, if I have, what cells do I, j, k dominate? Well, anything of the form I minus something, j minus something, k minus something, okay? And in principle, the longest common subsequence here is going to be, if the characters match one more than the longest thing that you could have realized up till here, okay? But what is the complexity of finding this? Okay? I'm going to say that it is just like edit distance that we have grown to love in the last hour or two, okay? Except that there are more cells that you are coming from, okay? In the edit distance, when we had 2 strings, how many cells were the possible predecessor of this cell that we had to look at in order to make a judgment? How many cells? 3. How many will there be when we go to 3 dimensions?
K plus 1.
Okay. Well, let's think about it. Okay, I claim that it's going to be 2 to the k minus 1. Okay, that the generalization is going to be, what is the next situation? The way I would draw it is that you kind of have a cube. I'm actually going to do a terrible job drawing this, so this is not going to go. What is it that's going to matter to me here? Okay, it's going to be the, this cell drawing is useless, so let's not look at this. Okay? But in general, what do I know? Every one of these things, it was either, these cells are going to be a combination of either keeping x the same or going back 1, and y being the same and going back 1. So there's they can't stay the same, but there's 2 choices for each possible dimension. Either I'm going back 1 or I'm not going back 1. In 3 dimensions, it's going to be the same thing. So there's going to be 7 cells that I need to look at in 3 dimensions, and 15 cells that I have to look at in 4 dimensions. Okay? So the number of cells that I have is going to grow exponentially with my number of strings. Okay, this is one thing to see. This is why I was weaseling, you know, a little bit on whether it was n to the k was the running time here, right? For every one of these, as k gets larger, you have more and more cells that you have to look at, okay? And so in general, for each cell, you have to look at 2 to the k, if k is the number of dimensions, 2 to the k minus 1 previous cells, okay, in order to update each cell. So the running time is going to be 2 to the k times n to the k as for k-dimensional string alignment. Any questions about that?
Can't you just see if you go back one for each dimension? Should make it like k times into the k.
Okay. I believe that this is 2 to the k times k. Oh, times n to the k.
But like, can't you just choose you don't need to like go back by one in multiple dimensions at a time. You could just like first go back by one in one dimension and go back by one in the other dimension. So you'll just like choose one dimension to go back by one. Can't you do that?
I believe that it's you have any subset of cells that you're going back from. Okay? Yeah.
Are we still computing the longest common subsequence, or is this another problem?
No, this is the longest common subsequence still.
In that case, I don't see why that shouldn't work. Like, you have two transitions, two possible transitions. One is ignore the last character of some string, and another transition is if you have the same character, the last character in all strings, then you can assume that. And that's k+1 transition.
Okay.
If you want to ignore two characters from two strings, you can just do two transitions.
Okay. Let's say I'm not going to argue with you here, okay? Because, again, okay, I may have simplified this to the point where it's a because of LCS, it may have gotten simpler. In general, the number of cells, I believe, is still 2 to the k minus 1. 2 to the k minus 1. If so, the important point is that if you have a complexity like this, okay, at some point, 2 to the k is going to be bigger than n to the k. For k equals, this issue isn't important for edit distance of 3 or 4 cells, or 4 strings, or 5, or any constant number. Because 2 to any constant is a constant, okay? When you get to a really large value of k, there is a question of whether it becomes the total number of cells is more than, how it relates to the total number of predecessors you have to consider, okay? Bottom line, this problem of multiple sequence alignment is an NP-complete problem, okay? The important thing to note is, for constant k, you can do this kind of alignment, okay, in a, in a polynomial time. But if I give you a large number of strings trying to find what is the longest common subsequence of all of these, this is an NP-complete problem. So it becomes exponential as k becomes a variable, okay? And that's the issue with multiple sequence alignment. Any questions? Okay. That said, let me now talk to you about what I consider to be my favorite dynamic programming problem and solution. Okay, I know every of you guys know a lot about dynamic programming. I want to show you what is, kind of my favorite dynamic programming problem, because it solves a problem that feels to me very complex. And in fact, we're going to see it's going to have a fairly simple solution once you get to it. How many people here, just to double check, know about context-free grammars? If you know about context-free grammars, raise your hand. If you don't, raise your hand. No farm with that. Okay, so this is good, okay? Context-free grammars are a very powerful way to recognize, to kind of encode patterns, okay? When you learned English, you probably learned something like a grammar, a set of rules that say nouns shouldn't be next to nouns, but nouns should be next to verbs. Okay? And a context-free grammar is a set of rules like this, okay, that describe how the structure of, let's say, a sentence is, okay? So, for example, here we're saying a sentence consists of a noun phrase followed by a verb phrase. That's great, but what's a noun phrase? A noun phrase is an article followed, meaning a special word that's like the or followed by a noun. What's a verb phrase? A verb phrase is a verb followed by a noun phrase. A verb was a word that does action, so things like drank or ran or killed, I don't know what I'm thinking about here, would be verbs, okay? And what's great about a grammar like this is it gives you a set of rules to describe what every, if this was the grammar for English, every legal English sentence would be. Now, English is not exactly expressible like this, but your favorite programming language is. Well, I don't know what, actually, maybe there's a good chance to ask, who here's favorite programming language is C? Few people. Who here says favorite programming language is Python? Who here's favorite programming language is Java? Who here has another favorite programming language? This is interesting to me. What is your favorite programming language? Rust. Someone else who had another programming language they liked that wasn't this. What?
Haskell.
Haskell, okay. Okay? Anyone else? Go. Okay, so everybody has favorite programming language. I don't know your favorite programming language, but I do know that the way that your favorite programming language is tells what is a syntactically correct program from a non-syntactically correct program is that they have a grammar like this. In C, what do we know? What is a C language program? A C language program is something that starts with a procedure name, and correct me if I don't remember this right, has something where there's arguments to it, has a left squiggle, has stuff, and has a right squiggle. That's a C language function, right? Now, how would you describe what is, the compiler knows what a legal C program is. How do you know that your compiler knows what's a legal C language program? When you give it one that isn't, it says you've got an error, right? A syntax error. So there is a piece of machinery in the compiler that recognizes what is a legal C language program. And the way that they specify what is a legal C language program is with a grammar like this, okay? And the act of recognizing what is a legal sentence gives you a tree like this. Does everybody see this? My legal sentence here is the cat drank the milk. Is the cat drank the milk a legal English sentence? Well, I can't tell you that unless you show me one of these trees. How do I know that it's a legal sentence? Because there is a tree that is rooted with the word sentence here. And what do we know what a sentence is? A sentence is a noun phrase followed by a verb phrase. How do we know that this sentence starts with a noun phrase? Well, a noun phrase has an article followed by a noun. The is an example of an article. Cat is an example of a noun. Does everybody see that this tree is kind of like a proof that this sentence is an English language sentence? Okay, it describes the rules. The grammar gives you the rules. The tree that it builds of how you apply these rules is a proof that that is a legal sentence or a legal C program. If you come back to, you type in a C program, you go to the compiler, it says it's a syntax error. You'll say, there can't be a syntax error. The way you would prove it to the compiler is you would take the rules for C, apply them in the right way, and prove that this program was a legal C program. Of course, if you do that to the compiler and the compiler rejects it, there isn't much you can do. Okay, but does everybody see that this is kind of the basis for how languages get recognized by computers? Any questions? Okay. So let's look a little bit more at these grammars. These grammars here, every rule is a variable name on the left. Okay. We call that a non-terminal. It's like a variable. It's not a terminal because it's not going to become a leaf. Up, boom. Okay? We say a terminal is a symbol, a special symbol that is fixed. Okay? Here, the, a, cat, milk, drank. Those are English fixed things. Those are like the ultimate leaves of my symbol, of my string. So the contents of the strings are the terminals. The variables that you define the names of the rules by are the non-terminals. Any questions about this with these grammars? Okay? Fair enough. Parsing is what they call, is the act of given a string and given a grammar telling me whether that string is recognized by that grammar. Some strings you write are C programs. Some strings you write are not C programs. Parsing is the act of telling what is a C program from what is a non-C program. Okay, any questions about that? And parsing is really the act of building this tree of rules, which we call a parse tree. The grammar is fixed, they gave it to you. The string is what you want to have interpreted. The way you're interpreting it is by building these tree of rules applications, such that you end up recognizing it properly. Okay? Any questions? Now, in algorithms for parsing, they pull a little bit of a trick in trying to say what the efficiency is. And so I want us to make sure we understand what this trick is. Okay? N is the length of the program. So if you have a C program, your program can be very long. Okay? You could have the program be 1,000,000 characters long, 1,000,000,000. You can imagine the program running the universe might be 1,000,000,000 characters long. N is the length of the program. How many rules are there in the C that define a programming language? Every programming language set of rules was written by a person, okay, the programming language designer. And this is fixed over all programming language, once you fix the programming language, okay? So programs can get arbitrarily big. The grammar is fixed size. So we're going to assume the grammar is of constant size, okay? Even though it has a lot of rules, I'm not going to count how many rules it has. Does everybody get this idea? We want to now know what is the complexity of recognizing a string of length n given a constant sized grammar, okay? How do we do this? How do you tell if something is a real C program or not, given all of these rules? Okay? When I was in college, they taught a bunch of these complicated parsing. I had to take a course in compilers. Does anybody take a course in compilers anymore? Some of you do. Okay, so some of you have seen this thing. And you may have seen all kinds of complicated parsing algorithms. They teach you about LALR parsing, all this kind of thing. Very, very messy stuff, okay? But actually, the algorithm for testing whether a program is matched by whether you can parse a string according to a grammar, that's actually a surprisingly simple algorithm if you look at it right, okay? What is the way to look at it right? Well, the first thing to note is that there is no grammar that has to have very complicated rules in it. Suppose I have a rule that said, like I said, a C program. What was a C program? A C program was equal to what? I think it said it was a function name followed by a squiggle. Maybe we'll call it a left bracket. Followed by a stuff. Followed by a right bracket. I think that's what a program is in C, right? Now this is a rule of 1, 2, 3, 4 non-terminals. Is there a way to turn a rule with 4 non-terminals into shorter rules? How would I turn this into a shorter rule? Okay, you're saying just cut it. Okay, well, what does cut it mean? What if I set up a new variable? Let's say I'm going to call it a C1. And I'm going to say C1 is going to be equal to LB stuff RB. Now, what can I make my C rule be? Does everybody see how I have made this rule now only 2 symbols, right? Now I push this away, okay? But you see how I could do this again and again and again until I make it so every rule is either going to consist of 2 non-terminals or maybe a non-terminal or maybe 1 non-terminal and a terminal, okay? Any questions about this? If the grammar was of constant size before I did this transformation, how big is it going to be after I did this transformation? What? Still constant. Okay, it's a bigger constant. But does everybody see that if I said the grammar was so tiny I didn't care about it, it's still so tiny I don't care about it. Okay? Any questions about that? You see how I did this transformation? Now every rule is either going to be of the form basically 2 variables, or a variable goes to a non-terminal. Okay? Any questions about that? They call this Chomsky normal form for whatever reason is for grammars. But basically, and it's probably because Chomsky did the first one to see it. Okay? So every rule in C language, to define a C language program, only has 2 variables in it. Any questions about that? How then can I now recognize whether a program is a string is recognized by this grammar or not? What is the algorithm for doing parsing? Okay? I claim we can do this by dynamic programming. And the key idea here is we're going to have a, a complexity where my state is going to be m of ij, x, is going to be true if there is a non-terminal x, okay, which is recognized by the substring si to sj. So what is my story? Here, I have my string, which is my C program, right? I think it probably starts main, kabunk, kabunk, squiggle, stuff, 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 squiggle, right? Okay? What is my rule going to be? Or what is the state of my dynamic program going to be? I'm going to say for every subrange, let's say from here to here, if this is I, this is J, okay? I want to know, is it true that the string from I to J can be recognized by non-terminal X? I think I called the non-terminal here stuff, right? Does everybody agree with that? So if this was a legal C program, from I to J would be recognized as stuff, okay? And M sub ij stuff is going to be true. Any questions about that? Okay? Now, what does it mean? Any questions here? Do people see this, or who's confused? Okay? Are you confused in a way you can ask me about?
I'm confused in a way I can't.
You're in a confusion. Okay, fine. Let's try it again. So, we're trying to figure out, we'd love to ultimately take my C program and on top of it build a tree where on the top is going to be C, okay, because it's a legal C program, and there's going to be different rules, right? One rule here that I said was that there was a function name, fn. Fn is ultimately going to be mapping to this part of my C program. Is that right? So I'm going to want Fn is going to have to go from 1 to this point. Let's call it, I don't know, let's call it Q for whatever reason. Right? And the left bracket is going to ultimately go to this part. Right? So we're going to be building ultimately a tree on this. We want to figure out how do we have an application of this tree of rules that describes this program. And what is the state? M of ijx is a matrix, okay? It looks like it's got 3 dimensions. The first is the starting position of a substring. The second is the ending position of a substring. The third is a non-terminal symbol, right? How many possible values are there for I? N. How many possible values are there for J? How many possible values are there for X? Constant. Although it's 3 dimensions, in fact, this is still only n squared symbols, right? So my matrix is only going to be of size n squared times a constant, okay, because I'm cheating with the size of the grammar. Okay, any questions about that? Okay? Now, if m sub ijx is true, that means that there is a rule labeled x with the property that it recognizes the substring from I to j, right? How can I do this as a recurrence relation to tell whether or not m of ijx is true? That's what you need to do with dynamic programming. You need something recursive. Can anybody think of what's recursive going on? Yeah?
You know that the non-terminal has 2 cases, so it's either other 2 non-terminals or just a terminal. If it's a terminal, you can just check. If it's 2 non-terminals, you don't know which part corresponds to the first one and which part corresponds to the second.
Right.
So you try to cut this.
Okay, so the interesting case is when I have a rule, here I had fin C1, that's going to be a rule of a non-terminal followed by a non-terminal, okay? And I want to know now, I want to apply that. If this is a legal C program, it contains a function name followed by a C1. Where is the breaking point between a function name and the C1? It's right over here. Does everybody see that? This is a legal C program if there is a place K where to the left of K it gets recognized as a function name, and to the right of K it gets recognized as a C1. Okay? People get that idea a little bit? I'm going to write the recurrence and it's going to look scary, but it's not scary. Okay? Let's look at this thing. What do I know? mx, okay, of ij, mijx, the substring from I to j, can be recognized by an x if there is a rule x goes to yz. Remember, all rules are going to have two non-terminals in it. Okay? Such that if there is a place, so over all rules of type x, which are going to have to, by definition, have two symbols, is there one of those rules, at least one of the rules that scores for an x, okay, such that, basically, there exists a position k such that the stuff to the left of k gets recognized by y, and the stuff from k plus 1 to j gets recognized as a z. Okay, I want people to understand this recurrence before I go any further. Okay, it's not really that hard, okay, except that there's a lot of symbols going on. Okay, what's this saying? If there is a rule, x goes to yz, okay, then, and if we're going to recognize the substring from I to j by this rule, what do we know? There must be a k such that from I to k it gets recognized as y, and from k plus 1 to j it gets recognized as a z. If there is such a thing, then there is a way to recognize I to j as an x. How many do people see that this recurrence is doing what I want? Who here? Any questions about this? I'm going to go a little deeper after this, so it's important that you get this if we're going to go any further here. Any questions about that? Okay. Okay. What is the running time of this? And for the non-terminal case, for the case where it ends in a symbol, if a symbol is ultimately one letter, what is the basis case here? We know that ij, the string from I to I, is recognized as an x if there is a rule, or they sometimes call a rule of production, x goes to a. If x goes to alpha and character I of the string is alpha, then the substring I to I gets recognized as an x. So everybody see that's the basis case of our recurrence. Okay? What's the running time of this algorithm? Okay, what is it? M cubed. Now, why is it n cubed? Okay, well, we've got how many cells are there in the dynamic? I always think of analyzing a dynamic programming algorithm. How many cells times the cost of filling the cell, right? How many cells are there? N squared. And where here is the other n? It's coming from here in the value of k. K goes from I to j. There's j minus I, which could be as big as n, possible choices here. Okay? What about this thing where I select for all the rules that call for a number x? How many rules are there? Constant, right? So that doesn't count, right? Does everybody see this? Okay? Again, so this is why this is an n cubed algorithm for parsing. Okay? Any question? How many people see why parsing a grammar is now n cubed? Okay? Any questions here if you don't? Okay? Because this is actually a powerful thing. Okay? And would have gotten me through my compiler's class if I'd known about dynamic programming then. Okay? Any questions here? Do you know other algorithms that are dynamic programming n cubed type algorithms? This is often the way that they work. You have a string, you pull out all substrings, you're then going to run it in between this. What is an example of an n cubed algorithm for a problem that you're used to that might be of this type? Okay, is there anyone that's, yeah? A big string into what?
Valid, like correct words.
I mean, like parentheses. Is this what we're talking about? Okay, so let's think what this is about. Have you seen the problem? How do you tell if something is well parenthesized? This might be a way of thinking about it. Okay, a well-formed formula, a wolf. Okay, a parenthesized string. What do we know? How do we know if this is well parenthesized? Well, one thing that's true is if it is, there is a left bracket and there is a right bracket. There is a place where, from here to here, okay, this is, the whole thing is a well parenthesized expression if everything to the left of it is well parenthesized and everything to the right of it is well parenthesized. Does everybody see that? That is kind of an n-cubed algorithm if you're looking for it to do it this way, okay? Wait 1 second. I know your question's going to be, so we'll talk about that. Okay? You could have expressed this grammar, this order of parentheses by these rules. A well-formed formula is what? There is a left and a right, and something inside has to be well-formed, or it's well-formed followed by well-formed. Okay? Any questions? Now, I know you can recognize whether something is legally parenthesized by just going from left to right and counting. Okay? So there's maybe a cleaner way of doing it. But there are algorithms like this. Now I'll take your question.
What I wanted to say is that I meant that you have a big string but without spaces. And you have a dictionary of valid words.
Okay.
You want to break the string into.
Okay, so you want it, right, okay, right. So you're saying you want to encode something based on this thing. You have a dictionary of words, okay? You want to express the text in terms of, is it a legally well-formed thing? There are other, if you think about it, in this case, in the formulation that he's talking about, let's just go back to this thing again. You've got a dictionary D, where you've got a bunch of words here, right? You've got a text, and you want to know, is there a way to make it, this text, expressed as parts of those words, okay? Now, it's not the case that the greedy algorithm works for this problem, right? You could have a word like, what is it? The word at is a word. Is there anything in English that begins AT? What? ATM, okay. It's not the greatest example, but fine, okay? So now if you have a sentence that begins ATM, okay, and you want to recognize it, can it be expressed in this language of words? Do you see that there's some confusion here? Okay? And if I want to find the right way to do it, there's lots of different ways I can apply words from my dictionary to this, right? There's potentially an exponential number of decodings, okay? That's, in this case, what's his algorithm going to be? He's going to want to know for every substring, is there a way to express it using his set of words? And so it's a lot like the problem that I'm looking at here. In fact, it may almost seem like, is there a context-free grammar like this? I think we're saying, if for this problem, is there a way to express that as a context-free grammar? We can say that a string is legal if it is equal to a word followed by a legal string, right? And what is a word that is legal? It is every one of these. W equals this, W equals that, W equals that. Does everybody see that if we had a constant-sized dictionary in some sense? We would be expressing this problem, could be expressed as a special case of my parsing thing. That's why parsing is powerful. And this ambiguity thing is why it's not trivial. That's the other thing that's important here. Some of you who may have just first heard of this grammar thing says, hey, why isn't this so easy? Why don't I just apply the rules in a greedy way? It's this ambiguity that there's multiple ways that rules can apply to different parts of the thing that makes this challenging. Okay? Any questions on parsing? It should be clear that we can parse these grammars in n cubed time if we, for any grammar, for any string of length n, to tell whether you are legal with the rules takes n cubed time. Any questions? This is a very powerful thing, but it's not my favorite dynamic program. What is my favorite dynamic program? Let me see if I got this here. Boom. What if I am given a program and a computer program that you have written, when all, you guys are very good, but whenever you type a program, is your program syntactically correct? Do any of you get compiler errors at this, or at this point you guys are too good for that? Okay? You guys have from time to time get a compiler error, right? Okay? Why do you get a compiler error? It's because what you typed in wasn't a legal program in that language, right? Now, for people of your skill, okay, it was presumably a few dumb things you did to make it, why it didn't parse. What if we want to now produce a program for this problem? Given a context-free grammar and a program S, or an attempted program S, that does not compile, what is the smallest number of changes you have to make to that program in order to make it legal? You see what the algorithm problem I'm trying to solve is? The input is some diseased program somebody typed in. Maybe they didn't know the C language very well. Maybe they were getting tired or careless. You want this program to compile. What is the smallest number of changes you can make to that program in order to make it compile? Okay? This is the problem that I'm now interested in. And this is kind of now an important, actually sort of an important task. How many of you have used these, sort of code pilot or these program generators? That, right, okay, it's going to, few of you have used it. Those of you who haven't used it, this is going to put you all out of business, okay? Because now these AI systems are building, writing programs for you. But sometimes the programs they write are not syntactically correct. This is learning, what they do is amazing, okay? But does everybody see what the problem I care about is? I give you a C program where there's now some number of places where they made a mistake in it. How do I find the smallest number of changes I need to make in order to make this thing compile? Okay? How do I do this? Can anybody think of it? This is kind of a little bit like, it should smell like my parsing, but it should also smell like edit distance, right? Edit distance is about the smallest number of changes, right? Okay, how do I do it?
So, again, we're going to have the state be a substring and the rule. And we're going to try, or rather a non-terminal, we're going to try all the rules that match that non-terminal. I'm going to try to cut the string in every single position. And what we're going to do is, we're going to return the amount of substitution that we need to do to make this work. Now in the base case, if we're going to be at a terminal, and if it matches the string at that position, then we just return 0. And if it doesn't, we return 1. And then in the recursive case, we're just going to take the minimum of all of them.
Okay, let's see what I think this is saying here. Okay? This recurrence relation looks a lot like the other recurrence relation you saw, right? What is the change that I have made? The main change, I said, is what my recurrence symbol means. M sub ijx used to be true or false. Can I parse from I to j and get x? Now what is it going to be? It's going to be an integer function that says for the string between I and j, how many changes do I need to make in order to make it parsable as an x? Okay? Now it's an integer function. It's no longer a Boolean. It's now an integer thing. And so now what is my algorithm? Simply, I can parse the string, the minimum number of changes I need in order to parse from I to j, ending up as an x, okay, is what? The min over all x rules of the min over all places where I can break of the number of changes to turn everything to the left of where I broke into a y, plus everything to the right of where I broke into a z. Does everybody see this? How many people see this? If you don't see it, you don't. How many people see it? Be honest with me. How many people don't see it? Okay, let's try it again, because first of all, it should be clear. This looks an awful lot like the other recurrence, right? Okay? What is it saying? Let's go back to the parsing thing again. Okay? How do we know, prove to me that from I to j, the substring from I to j, that it can be turned into an x? That it is an x, recognized as an x. If it is an x, then there is a rule of the form x goes to yz, and there is a place k to break my string, chop, 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 where everything to the left of it was a y, and everything to the right of it was a z. If everything to the left of this breaking point was a y, and everything to the right of the breaking point was a z, then I can apply rule x is equal to a yz. Okay? How many people understand this recurrence for parsing? How many people are confused by this recurrence for parsing? It's okay to admit it. Any questions about sources of confusion? Okay? Once you see this rule, okay, now keep that in your eye while I go bunk, bunk. The recurrence looks almost the same, right? The main thing here is now instead of being a Boolean function, it's going to be an integer function. And it's going to keep cost. What's the smallest number of changes from I to j that will let it become an x? Okay? What are the smallest number of changes? Suppose I have something like this. What's the smallest number of changes it takes to turn this into a C program? Does anyone know? What would be the smallest number of changes? I probably have to write an I, an N, a kabunk, 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 kabunk. That would be 1, 2, 3, 4, 5, 6 changes, right? That's how many changes it would take to turn this into a legal C program, yeah?
Yeah, I have a question. If you allow insertions like that, not only substitutions, don't you need to consider the empty string as a base case? Like,
okay, so the empty case has to be a base string. How many changes does it take to turn an empty string into a C program? Well, first question is, does the compiler accept an empty string? I have never tried this, but I think the answer is no. It depends what the grammar is, right? You could imagine the grammar said, I will accept an empty string and knock off work early because there's nothing for me to do, right? But you're right, the basis case here is going to include the cost of editing from an empty string. What would be the empty string? The empty string would be I equals 0, j equals 0, right? So that's the basis case you're looking for.
and how do you compute it for the base case? Like, for the base case would amount to what's the smallest string that matches each.
Okay, well, okay, so What's the cost of, I see, so you're saying I would have to know in advance what the length of the shortest legal string is, okay? What?
For each rule. For each
rule, okay? So that would be the basis case. And I will claim that for most rules, this is not in most reasonable grammars, this shouldn't be a hard thing to do, okay? In this case, we are saying we understand the C program is this, but it may very well be a C may well accept an empty string. You know, empty strings are usually okay things to accept. People like empty strings, okay? So I see what your point is, but I'll say it doesn't bother me because for just about any rule in any grammar, it should be pretty easy to figure this out. And usually it will be the empty string is the shortest legal thing to be there. Okay? Any questions? Okay, so what is the recurrence? Let's just go through it one last time. Okay? The minimum number of changes to turn this into an x. Well, I'm going to have to apply a rule that recognizes x, and I'm going to have to find a place where it splits. The cost for any split in any rule is the cost of editing the left stuff to a y and the right stuff to a z. Okay? So this is, what's the running time of this algorithm to fix any string and turn it into a legal program? If the string is n, this is going to be n cubed. The same time as recognizing is to actually figure out this number of changes you need to make it legal. And this I find kind of amazing. This is kind of a hard-sounding problem to me. And it's solvable by the same kind of cheap recurrence relation that I've got over here on the slide. Any questions about parsing or anything like this? Yes?
In terminals increase the complexity?
What?
You still have to know if any given substring can be terminal.
Right.
Is that
okay, you're saying it's hard to know if a given substring is a terminal. Well, how big is my grammar? My entire grammar is what? Constant. How big is my biggest non-terminal string? Constant. Okay, it's part of my grammar. Look over here. See it over here? See that over there? Drank. That's what you're saying. If the whole grammar is of constant sized, then the longest non-terminal symbol in there is of a constant size. So what's the cost of recognizing if a substring matches that non-terminal? Constant. Okay. So you know so in general, when you're building these grammars, you're not building them with huge, complex, infinitely long symbols. Okay. If you want to recognize something infinitely long, you build a rule to do it, not embedded directly in the grammar. Okay? Any other questions about parsing? Yes?
I imagine there's a way for like a string to be recognized by more than one tree.
Yeah, so there's this question of, is there only one tree that recognizes a string? And the answer is no. Okay? Or in the fullness of complexity of grammars, there are things called ambiguous grammars, where there are multiple ways of recognizing it. Okay? There's not necessarily only one tree for any string. In an arbitrary grammar, there might be many different trees. We're asking, is there a way to recognize it? Or what's the smallest number of changes till you get a legal parse tree? Now,
would be, is there a way to systematically check a grammar is not ambiguous? Because I imagine it would be useful in designing.
Okay, so you're saying, wait a second, if I want given that there might be multiple trees that recognize a string, and you're saying that might be bad. Is there a way of recognizing whether or not of designing a grammar that is not ambiguous The answer is that this is the kind of thing people worry about when you take a compiler's class or a automata theory class. Have people taken how many people here have taken a course in theory of computation, automata theory? And did they talk about grammars and stuff like that? And did they talk about ambiguous and non-ambiguous grammars? Okay, so this is something that, yes, this is an interesting question. Now, part of the issue then is when you are designing a programming language, one of the things you would like to do is for this grammar to be non-ambiguous. Okay? So there's certain rules sets of rules might be ambiguous. It's possible to design grammars that are not ambiguous. Okay? And this is one of the things that you worry about when you're designing these things. The other thing that you worry about, just for general education, is do you want your C compiler to run in n-cubed time? Okay? And the answer is no. That discourages you from writing long programs. Maybe for the contests you want the C compiler to run in n-cubed time so you can encourage you to write short solutions. So you really would like your programming language not only to be recognized by a grammar, but you'd like it to be recognized by a grammar that's simple enough that it doesn't require the full power of this kind of an algorithm for it. Remember I gave you this grammar for recognizing parentheses. Do you need a context-free grammar parser to recognize a legally parenthesized sentence? Actually, no. You really have to count whether or not you have more left parentheses than right parentheses. So parsing the parentheses language was in fact linear in the length of the string, right? So what is the solution? If you are trying to write your own programming language, what do you want to do? You want to design the grammar for it in a way that one of the simpler algorithms for parsing works. For general context-free grammar algorithm, there's no better way than to do it in n-cubed time. Okay? So it's not like this is a fake thing I'm showing you that everything can be done more quickly. But for simple enough grammars you can do quicker, and if you were designing your own programming language, you probably want to design it so that it can be parsed in a simpler way. And what is that simpler way? Remember I was mumbling about LALR parsing and all these kind of things? Those are subsets of grammars that are easy to parse. That there's a fast algorithm. If you have a grammar that looks like this, it will not be ambiguous, and you can parse it in some easier way like you parse the left-right parentheses. Okay? Fair enough. Any other questions about parsing? Yes?
As curiosity, but is there an algorithm for checking, given a grammar, a context-free grammar, whether there is any string for which it is ambiguous?
So is there, this is one that I might have been able to answer when I took my automata theory class, 35 years ago or 40 years ago. Does anyone know this? You guys seem to be a smart crowd.
I think it's NP-complete.
To tell whether a given grammar is okay, so he's saying that he thinks it's NP-complete. I don't know what to think. But I do know that there are techniques for designing grammars that will not be ambiguous. Okay? And so you can then prove for your grammar that that particular grammar is unambiguous. Okay? So this is a problem we have. Okay. Now we have to talk for 3 more minutes. And either I can introduce a brand new topic, or we can have another question about parsing. Topic? Okay. Okay, I think that's a minority view, but let's just ask. Okay. Anything that we want to talk about? Any questions about this? Okay, let me ask one other question. So, next class I was going to start talking. I was going to talk about network flow, but I still have things on suffix trees and things like that. Are people interested in hearing that? Yes, okay, so what I am going to do is, you will get some network flow tomorrow, but you're also going to get some more sequences, whether you like it or not. Okay? Any questions? Any other questions about parsing or grammars or anything like that? Yeah.
Is it okay to have a rule that is made out of more than one?
Non-terminal.
Yes, but I want to say, for example, the C is equal to Fn C1. But do you have the rule that C is equal to Fn C2, for example?
Okay, say this again, 'cause someone who's translating this for me. Tell me what this says.
I think he was saying like, I didn't hear him.
Try it again, try it again.
Yes, the question is if you can have a rule that has more than one way to be formed.
Okay, so the question is there, you're saying that I did this transformation, and I said, look, I said that I translated, I had A, B, C, D, and I translated it to C prime, and said C prime was equal to B, C, D. Is there more than one way I could have done that? And the answer is yes, because I could, for example, have bitten the last rule off. I could have alternately written it as C is equal to XD, and X is equal to ABC. You see what I mean? So I could have actually done this decomposition in many ways. Okay? By convention, I did it from the start. Does it make a difference? Well, it can't make any difference because what do we know? How big was the grammar? Any way we do this, is it going to be constant? Okay. And it's just going to be, I'm creating new symbols for this. So there's never any ambiguity about what I'm doing. I'm creating new symbols at every point. Any way I break that up would be fine. If you really wanted to get exciting and make a separate rule for this, okay, you could have done that also. But I find that going from left to right was the easiest thing to do. Okay, anything else that's important? If not, I think I've used up my time now, and we can move on. Okay, so thank you. Today you've got a contest on dynamic programming. I hope that this is good, and I will see you guys tomorrow, I guess, and we will resume there. Is there anything that the organizers need to say? Or